In this tutorial, we are going to talk about the quantum mechanical model of the atom. So first we will talk about the history of the quantum mechanical model, and then we will describe the quantum mechanical model, and then we'll talk about how the electrons are organized within an atom according to the quantum mechanical model. The quantum mechanical model is the most current model of the atom. Sometimes it's referred to as the cloud model of an atom. And here's a couple of pictures of some different quantum mechanical models for different atoms. Our quantum mechanical model comes out of what we know about light. So if you remember, light has both particle and wave behavior. And Einstein actually proved that and won a Nobel Prize for it. And later, Louis de Broglie sort of applied that same thing to matter and said that matter also has particle and wave behavior, and that the smaller matter gets, the less and less it behaves like larger matter, especially electrons. And it was Ernest Schrödinger who actually developed a mathematical equation that is capable of describing the energy and the position of an electron within an atom. We should probably also mention at this point, not only Ernest Schrödinger, but Heisenberg. Heisenberg was also responsible for adding to this theory about electrons and their energy and position. And we'll talk about him a little bit later. So let's describe the quantum mechanical model. So the quantum mechanical model is different than the Bohr model because it says that electron energies are quantized, which is the same thing that Bohr said. Bohr said that energies of electrons are quantized, but he just thought they were quantized into energy levels. And he called those orbits, right? He said they orbited in these fixed little pathways. But in the quantum model, instead of orbits, there are these things called orbitals, and instead of being a nice fixed little pathway, orbitals are a three-dimensional region of space where an electron of a given energy is most probably found 90% of the time. So it means that you'll likely find it there, but it doesn't necessarily mean that it's going to be there. And we talked about that in the last chapter. So another way to say that is that the position of an electron is uncertain, and that all we can really do is tell or describe where it might be or where it probably will be based on probability. And this is basically the Heisenberg uncertainty principle. So remember we talked about Heisenberg earlier. His uncertainty principle basically said the same thing, that you can't know the position of an electron and its energy at the same time. You can either know one or the other, but not both at the same time. So all we can really do is discuss the probability of finding an electron of a certain energy in a certain region of space. And, we can go back over and look at these pictures of these quantum models. And these quantum models are drawings to help us kind of understand what the quantum mechanical model of an atom looks like. And you can see that these dark regions, or that are more dense, these are our areas of probability. These are our orbitals. This is where we're likely to find electrons 90% of the time. Wherever it's dark, that's where electrons spend most of their time. All right, so let's discuss the organization of electrons within the quantum model. So we're going to keep this as simple as we can, and it is a lot of information, but you're going to be okay. So first of all, we talk about the principal quantum number, which is the same thing that Bohr described as being energy levels. Technically, there is an infinite number of energy levels or principal quantum numbers, but most of the time, atoms have 7 or less. And we number them. N equals 1, N equals 2, N equals 3. And you've seen this before in the Bohr model. So here's a picture of the principal quantum energy levels for an atom, according to Bohr anyway. So within an energy level, you will find these things called atomic orbitals. And sometimes I refer to atomic orbitals as a sublevel. And what they are regions of space where where there's a high probability of finding an electron. And they have letter designations, and those letter designations are S, P, D, and F. All right, so this is what an s orbital looks like. An s orbital is a spherical shaped orbital, and you can imagine that the nucleus is there in the center, and it's a region that's spherical shaped where you would find, or might likely find, electrons. S orbitals, there's only one type of s orbital, and they can hold 2 electrons each. These are p orbitals. P orbitals are dumbbell shaped, and there are 3 types. You have the ones that are called px. So this is px because it's on the x plane, right, if you're looking at 3 dimensions. And then you have the py. So this is py, and then pz. So they can exist on 3 different planes of existence because we are, in 3 dimensions. And they can hold 2 electrons each, which means that a p orbital or a p sublevel can hold a total of 6 electrons because there's 2 in each orbital and there are 3 orbitals. All right, these are your d orbitals. And there are 5 d orbitals, and you can see that they're oriented, most of them look like clover leaves, and they're oriented on the axes, either the x, the y, or the z axes of 3-dimensional space, and then in between the axes as well. You don't need to know the designations like you did up here for the x or for the p orbitals, but you do need to know that there are 5 types of d orbitals. They can hold 2 electrons each. Therefore, they can hold a total of 10 electrons in the d orbitals. And then lastly, there's the f orbitals. And again, you don't need to know the f orbitals designations. You just need to know that the f orbitals, there are 7 f orbitals, or 7 types. They can hold 2 electrons each. Therefore, they can hold a total of 14 electrons. And your d orbitals are weird looking and they're totally funky shapes. And in no way am I going to make you draw a d orbital, an f orbital. And here's a summary of the orbital types. So remember the s orbitals, there's only one type of s orbital. It's the spherical shaped one, and it holds 2 electrons total. P orbitals, there are 3 p orbitals, px, py, and pz on the 3 different planes, and they can hold 2 electrons each for a total of 6 electrons. D orbitals, there are 5 of them, and they hold 2 electrons each for a total of 10 electrons. And the f orbitals, there are 7 of them. They hold 2 electrons each for a total of 14 electrons. So something that's really interesting is that the number of sublevels that are within an energy level happens to be equal to the principal quantum number. So for example, energy level 1, n equals 1, only has 1 sublevel, which is the s orbital. Energy level 2 has 2 sublevels, an s and a p. Energy level 3 has 3 sublevels, s, p, and d. And then energy level 4 has 4 sublevels, s, p, d, and f. And I think you get the idea from there. So I'm about to do a little analogy of how electrons, or how the orbitals are arranged using a hotel. So this analogy is going to be based off the idea that an atom is like a hotel, which it's not, but let's pretend that it is. So we're going to consider the nucleus of this hotel to be somewhere in the basement. And then you've got different floors. You've got floor number 1 and floor number 2, floor number 3, floor number 4, and floor number 5. And we could go to an infinite number of floors in this hotel. We're actually going to stop at 4, but you get the idea. All right, so floor number 1, n equals 1, is like the first energy level of an atom. It essentially has one room, and that room is the S room. And in that room is a bed. And that bed, 2 people can sleep. Now, in this case, it's not people, it's electrons. So these little arrows that I've drawn, there's an up arrow and a down arrow. Those little arrows designate electrons, and the reason we draw one up and one down is because electrons cannot spin in the same direction. So you just need to know the arrows mean electrons, and that you always point one up and one down within an orbital. So remember, our s orbital can only hold 2 electrons. Our first energy level only has one orbital, an s orbital, and it can hold 2 electrons. And we're going to call this the 1s orbital. All right, energy level 2 has 2 rooms in it because it has 2 energy levels, or 2 orbitals, or 2 sublevels. It's got the 2s orbital, and it's got a 2p orbital. Now remember, the 2s orbital only has one bed, or one orbital, and it can hold 2 electrons. So 1 electron, 2 electron. Now, the p sublevel, or the p room, has 3 beds in it. So if you remember, we've got the 2px, the 2py, and the 2pz orbitals, and each one can hold 2 electrons. 1, 2, 1, 2, 1, 2. So that gives us a total for the people that you can put, or the electrons you can put into n equals 2, or energy level 2, as being a total of 8 electrons. And by the way, energy level 1 could only hold 2. All right, let's move on to energy level 3. So energy level 3, remember the quantum number 3 means there's 3 sublevels. So there's going to be an S, a P, and a D. So you're going to have a 3s orbital, a 3p orbital, and a 3d orbital. Your 3s orbital can hold 2 electrons, so 1, 2. Your 3p orbital, there are 3 of them. And if you remember, they are the 3px, the 3py, and the 3pz orbitals, and they can hold 2 electrons each. And then the d orbitals, there are 5 of them. And remember, I told you didn't need to know the names or the designations for those orbitals, but you do need to know that each one holds 2 electrons. So that gives our third energy level of the atom, or our third level of this hotel in our analogy, a total of 18 electrons possible. All right, we're going to stop at 4, and I'm going to go ahead and just fill it in, not while I'm talking. And so you can see that the 4th energy level has 4 sublevels, the S, P, D, and F. And the S sublevel has 1 orbital with 2 electrons. The P sublevel has 3 orbitals with 2 electrons each. The 4D has 5 orbitals with 2 electrons each. And the 4F has 7 orbitals with 2 electrons each, which makes this a total of 32 electrons that can be held in that energy level, the 4th energy level of an atom. So in theory, the 5th energy level would have 5 sublevels, and the 6th would have 6, and the 7th would have 7. But in fact, that's not really what happens, and we'll talk about that a little later when we talk about electron configuration. But just really quickly, I want to kind of write down a quick little electron configuration just to kind of wet your feet. So for energy level 1, we would give it this electron configuration, 1s2. There's 1s orbital with 2 electrons in it. For energy level 2, we would say 2s2, 2p6, because the 2s has 2 electrons and the 2p has a total of 6 electrons, and so we write it as 2s2, 2p6. Energy level 3 has 3s2, so 3s2, 3p6, and 3d10 electrons in it. And then the fourth energy level is 4s2, so 4s2 electrons. The 4p has 6 electrons in it. The 4d has 10 electrons in it. And the 4f has 14 electrons in it. And it should be noted that just because, like for example, the second energy level can hold 8 electrons, just because it can hold 8 doesn't mean that it will. It can be partially filled. Or the third energy level, just because it can hold 18 doesn't mean it's going to hold 18. It's just like a hotel. With a hotel, you know, when you book a hotel, you don't have to fill every room. And the fact of the matter is that with atoms, every room or every orbital doesn't have to have electrons in it. So in class, we're actually going to talk a lot about how the electrons fill the orbitals and in what order. But we'll save that for class time. So that is pretty much everything you need to know right now anyway about the organization of the quantum mechanical model.